apologies, we had a little bit of a delay there, but welcome in. We're very happy to have all of you with us today for Advanced Averaging Transverse Strain Measurement for Automotive Sheet Metal, sponsored by Instron. I'm Bob Brockler, the webinar coordinator with ASM International. We're very happy to have all of you with us today. If you have any technical difficulties today, dial 877-582-7011. That's going to connect you directly to a GoToWebinar technician. I'll put that number into the chat in just a moment as well. All of our attendees are going to be in a listen-only mode during the presentation. Please do feel free to submit a question at any time by using the questions window, and we'll get to as many questions as we can at the conclusion of the presentation. Abstract submission continues through November 15th for Aeromat 2026. Join us in West Palm Beach, Florida, USA for a wide range of technical topics, offering insights, and my slides are jumping around on me, sorry about that, into the latest aerospace materials and process developments with keynotes and panel discussions highlighting cutting-edge advancements and future trends in the materials community. Find out more by clicking or choosing the QR code on your screen, and I'll put a link to that conference in the chat in just a moment as well. Instron designs and manufactures high-precision systems for testing the mechanical properties of metals, composites, polymers, and other advanced materials. For over 75 years, quality engineers and R&D laboratories have relied on Instron equipment to deliver accurate, repeatable results across tensile, compression, fatigue, impact, and structural testing applications. Engineered for safety and reliability, Instron systems are backed by a global support network offering calibration, verification, training, and localized service, ensuring optimal performance in demanding materials testing environments. Our speaker today, Dean Lovewell, is the Materials Market Manager at Instron. He holds a master's degree in Materials Science and Engineering and a bachelor's degree in Mechanical Engineering from the University of Pittsburgh. Dean serves as the head of the U.S. delegation to ISO TC 164 SC1, that's the subcommittee on uniaxial testing of metals, and is an active member of multiple ASTM committees focused on the characterization of metals. With a background spanning both mechanical testing and metallurgical engineering, he brings a practical perspective to how metals are processed, tested, and applied across applications and industries. Before I turn this presentation over to Dean Lovewell, I do want to make a note that there are 2 downloadable documents in the handouts section of your webinar player. Specifically, these are 2 product sheets for some of the equipment that's going to be discussed today, and I definitely recommend downloading those. They'll be a great complement to the material that we're going to cover today. And with that, Dean Lovewell of Instron, I'm going to turn this webinar over to you.
Great, thank you, Bob. And good morning, everyone. Thank you for joining the webinar and spending some time with us today. My name is Dean Lovewell, and I am the Metals Market Manager here at Instron. At Instron, we manufacture equipment that's used for the mechanical testing of lots of different materials in various conditions for lots of reasons, from research to quality control. Now, one of the more specialized areas we operate in is the characterization of formability of sheet metals used in the automotive industry. Specifically today, I'm going to talk about the determination of R value, or the plastic strain ratio, as determined by either ASTM E517 or ISO 10113. Now, in terms of the history of metallurgy, the study of R value is actually fairly recent. The theory was largely developed around the 1950s, and the standards are even more recent than that. Now, one of the trends that we've seen in this field is really an increase in the complexity of determining R value. And this is directly due to the increased complexity of the materials themselves. During this webinar, I'll give a general overview of what R value is, how it's determined, and why the complexity of its measurement for automotive sheet metals has grown. And I'll, of course, discuss Instron's solution for addressing that complexity. So starting with a quick overview of plastic strain ratio. Plastic strain ratio or R value, is a measure of how a sheet metal behaves when it's stretched, specifically how resistant it is to thinning during plastic deformation. Now, a high R value means the material deforms preferentially in the plane of the sheet. That is, it spreads outward instead of getting thinner. And that's what we want for good drawability in forming operations. Materials with low R values, on the other hand, they tend to thin out more easily, which increases the risk of tearing or fracture during forming. Now, R value is determined from a tensile test, the same type of test that's used to determine other properties like yield strength, tensile strength, and elongation. One notable difference, though, is that the formula used is based on true stress and true strain data. Now, in practice, we almost always view and discuss tensile data in terms of engineering stress and engineering strain. This distinction matters because while engineering strain is based on the specimen's original dimensions, true strain accounts for the continuous reduction in area that occurs as the material deforms. Similarly, true stress uses the instantaneous cross-sectional area, giving a more accurate representation of the actual load-carrying state of the material. Now, the reason R value must be determined from true strain is that it specifically represents a ratio of instantaneous plastic strains in different directions, which these evolve continuously during deformation. Now, when setting up R value calculations in Blue Hill, you don't need to make any adjustments for this difference. Our software automatically converts the engineering stress and strain values directly to the true values used in this calculation. These calculations can be confirmed by referencing the Blue Hill help file, which you can navigate to from any Blue Hill screen. And these formulas match the requirements of the common industry standards, and they're particularly useful anytime you need to discuss how a particular material property was calculated. One key area addressed in the help file is the question of elastic strain. As both ISO and ASTM require that we remove elastic strains in the determination of R value. This is really important because, as I mentioned, this is the same tensile test where we're determining tensile strength and elongation. So we're also expecting the test to proceed beyond the range where R value can be determined. This means that when we need to, this means that we need to automatically subtract these elastic strains during the test. Now, when creating a method with a template R value, this is automatically factored into the calculation. However, our flexible software also allows you to build your own value, own R value, in which case you want to make sure that you enable the remove elastic strains toggle switch if you're planning to follow the standard for that test. So getting back to the calculation, we're measuring how much the specimen's width changes compared to its thickness as it's pulled in tension. This ratio, the width strain divided by the thickness strain, defines the plastic strain ratio. In automotive sheet metal, R value is one of the key parameters that tells us how well a material will perform in deep draw or stretch form applications. Understanding and accurately measuring it helps manufacturers predict formability and update their processes. As you could guess from its name, the plastic strain ratio is determined during the strain hardened region of the stress strain plot. During this part of the test, dislocations within the metal are moving. And as they move, new dislocations are being generated. Now, the rate at which a metal can create and store dislocations, and thus the extent to which it can strain harden, is directly dependent on its microstructure, which is in itself dependent on the composition. This is why some alloys exhibit PLC, some don't, and some only do under specific conditions that lead to a PLC-affected microstructure. Now, one of the reasons why 5000 series alloys are really well suited for automotive structural applications is because their microstructure enables a lot of new dislocations to be generated during plastic flow. This enables them to be significantly strengthened during cold work. 6000 alloys, on the other hand, flow much more continuously. However, while the magnesium in 5000 alloys is in solid solution and able to flow, the magnesium in 6000 alloys is tied up in magnesium silicon precipitates. These precipitates impede the movement of dislocations as well as the creation of new ones. And this explains why 6000 series alloys aren't really suitable for applications where a lot of strain hardening is needed to meet final properties. Now, although higher R values can be achieved by controlling the orientation of crystalline grains, which thus reduces barriers to deformation, there are really limits on what is possible for each microstructure. Now, the two most commonly used standards for determining R value are from ASTM and ISO. ASTM E517 was originally published in 1981. The normative reference for this standard is E8. Now, by normative reference, I mean that the testing performed to this standard follows E8 in every way, with only the necessary requirements to measure plastic strain ratio included in this document. This means that for test control methods, specimen dimensions, terminology, really anything besides plastic strain ratio requirements, your lab should refer to ASTM E8. The committee responsible for this standard is E2802, called the Committee on Ductility and Formability. We're actually meeting next week in Atlanta, so if you're joining the E28 committee meetings next week, please don't hesitate to say hi. It'll be great to talk to someone who attended the webinar. Now, the ISO version was first published their standard on plastic strain ratio in 1991. And at the time, it was just 3 pages long. Now it's 24. So there's certainly been a lot of clarification in this space since then. Like ASTM E517, ISO 10113 also has a normative reference. This describes all aspects of testing to ISO 6892-1. Besides the determination of the plastic strain ratio. This standard is the responsibility of ISO TC164 Subcommittee 2 on ductility testing, and we meet once a year, typically in September. One word of caution here is that attending this webinar is unfortunately not a substitute for reading either standard in order to confirm that your lab is in compliance. So if you're testing R value to ISO or ASTM, I recommend staying up to date with the latest publication. At the end of this webinar, I'll be providing my contact information. So if you have any questions about the testing in your lab or how to start doing this test, please don't hesitate to reach out. As the metals market manager at Instron, working with our customers to ensure that their testing is optimized for accuracy, repeatability, and reproducibility is really the most important part of my job. So if you have any questions or would like to discuss, I'd be happy to schedule some time with you and your team. So this diagram from ISO 10113 shows the profile of a strain specimen in tension for different R values. On the top, specimen number 2, we see the effect of an R value greater than 1. So this material would be resistant to thinning. As it's stretched, it would tend to spread more outward in the width rather than get thinner. So this material has good drawability and would be a good fit for a part that required forming into complex shapes or where a lot of strain hardening was desired. In the middle, where R equals 1, the width strain and thickness strain, they're about the same. Here, the specimen deforms uniformly, both in its width as well as in its thickness. And then down at the bottom, where R is less than 1, this material would spread much less, as it deforms preferentially in its thickness. Now, this diagram from ISO 10113, sorry, that was a previous slide. So as I mentioned, R value during the strain hardened region of the test. So after all yield properties have been determined, but before the onset of necking occurs, immediately after tensile strength. The reason why we don't calculate R value from the portion of this curve after tensile strength is because the formula for R value assumes that the width strain is relatively homogeneous throughout the reduced section. After necking occurs, width strain is localized to the position of the neck, so the formulas we use don't apply. Now, R value can either be reported from a single location, for example, when tensile strain equals 10%, or it could be calculated over a range like 15 to 20%. The specific requirement here is typically determined by the metal former, as they'll want to know the R value over the expected strain domain used in the manufacturing process. Now, the important takeaway that I really want to emphasize here is that once tensile strength is determined, so the maximum force has occurred, and after which you have the onset of necking, we can no longer use the R value formulas from ASTM and ISO. This is because the resulting width is no longer reflective of the width of the reduced section. This is because after necking, all of the width strain now occurs where the neck has started. So we see 3 different stages of the test here. On the left, we have a specimen in the elastic region. The strains in this region will be automatically removed for the Blue Hill calculation of R value. Then we have the strain hardening portion of the test, showing where B sub 1 would be measured. And then the final specimen on the right, this is post-tensile strain determination. We see that some necking has developed, and we know that as the test proceeds from here, all of the width strain is going to occur where that neck is. So whether the arms would happen to be at the location of the neck or elsewhere, it's still true that the transverse strain that they are measuring is not representative of the gauge width. So that was an overview of what plastic strain ratio, or R value, is and how it's measured. Now let's look at a material that really complicates our determination of R value. One of the trends that we've seen in automotive sheet is a transition from easily formable alloys to more complex alloys capable of achieving higher strengths in thinner cross sections. This includes the transition from interstitial free seals to advanced high strength seals, which I'll touch on at the very end of this webinar. It also includes an increasing shift to aluminum sheet. Now, aluminum is lighter than steel, and it adds some additional corrosion resistance, which is a really nice benefit for us here in Massachusetts, faced with both the salt from the ocean and the salt on the roads. But it's not without its challenges. To achieve the strength requirements for structural bracketry and body and white panels for automotive applications, aluminum is alloyed with magnesium to form a 5000 series alloy. This family exhibits rated yielding behavior as they strain harden, and this behavior is called the Portevin-Le Chatelier effect. And we see that effect here in the plot of this 5182 aluminum on the right, in contrast to the stress strain plot of the simpler dual phase automotive steel on the left. Now, the Portevin-Le Chatelier effect reveals itself just after yield, and in this 5182 aluminum, it continues all the way through tensile strength. Since this is the region where formability is characterized, it introduces significant variation to the calculated result, depending on which points are included in the calculation. Like I mentioned earlier, metal formers generally want a higher R value because it means they can get more draw out of the same material. Having a higher R value means the former will not only be able to obtain the shape they need, but it also means they'll benefit from the strengthening that occurs from the cold work used to achieve that shape. During tooling design, the R value along with the finished geometry will both be considered for how much work can be done without risk of excessive thinning. For this reason, it's important that the plastic strain ratio falls within a defined window. Non-conforming material, of course, risks being overworked, which can lead to cracking, or underworked, which would result in insufficient work being done to develop the strength desired. Now, although the calculation here defines the ratio as transverse strain divided by thickness strain, testing standards clearly specify that R value is not typically characterized from the direct measurement of the thickness. This is because it would be extremely difficult to measure the change in thickness for thin sheet metals. Rather, an axial extensometer measures the strain in the length, and a transverse extensometer measures the strain in the width. And by the law of constancy, the strain in the thickness is inferred. This is spelled out in the formulas in ISO 10113, as well as in ASTM E517. Now, in this visual, we're showing how Instron's automatic contacting extensometer, the AutoX, measures axial strain using the two arms connected to the main unit on the right, and the transverse strain using the smaller arms that meet up with the red dots in this illustration. You can see that a bit more clearly here if I remove those labels. In non-PLC affected applications, the AutoX with an added-on biax unit is an excellent solution for characterizing formability because its operation is automated, so it's effective at removing the variability that occurs from the less repeatable engagement that you get from a clip-on extensometer. Now, for materials with stable plastic flow, this method of a single width transverse extensometer is sufficient, since for the domain of the strain hardening region, which we see in this graphic, the width strain is homogeneous. You can see that the area between the green gauge marks reduces uniformly, and so the red dots are sufficient to provide the representative strained width. And then just another reminder here, you can tell that this is the reason why R values never calculated belong past tensile strength determination, since again, after the specimen has received maximum force, it'll neck locally, and those red dots will no longer be representative of the full specimen. So The PLC effect complicates this method by what's observed as jerky flow of the specimen. This jerky flow is the result of magnesium atoms diffusing through the aluminum matrix, pinning dislocation movement in localized regions of the specimen. With dislocation movement pinned, there'll be a rise in tensile stress, and we observe that in the curve. And that rise continues until the solute atoms become depinned, in which case they flow and the stress is lowered. This occurs repeatedly, and the striations are even visible on the specimen itself. These striations are called Luder's bands, and they represent localized regions of plastic deformation. What we're seeing on that specimen actually in this picture, and this is showing the periodic mismatch in surface condition between the regions of localized strain. Now, not only is this bad for surface quality finish, but it also really complicates our formability testing. This graphic demonstrates how this effect interferes with reliable plastic strain ratio determination. As the test proceeds through the strain hardening region, we see the pinning and unpinning in the sawtooth character of the stress strain plot. Each stress increase corresponds to the gradual pinning at dislocations, followed by a sudden decrease as they're released. Now, when we look at just the transverse strain data of this single width gauge extensometer, this is showing the strain that's observed in the width of the specimen. You can see that the width strain increases when the location of when the location of the strain is specifically at the transverse extensometer's arms, but then it plateaus while this width strain is occurring elsewhere. We know that during these plateaus, the specimen is continuing to strain in its width. It's just occurring in a localized band outside of the view of our single width gauge extensometer. Now, since we're missing the influence of that additional width strain on our R value calculation, that means that our calculated R value is going to drop throughout that plateaued period, as the formula assumes that the additional strain must be occurring from somewhere else. It doesn't see it in the width strain, it doesn't see it in the axial strain, and so it assumes it's coming from the thickness. This leads to large swings up and down in our R value calculation. Now, Liu et al. Developed a model for this behavior that I find really clarifying. Beginning with figure A on the left, we have an aluminum magnesium alloy in tension in the elastic region. The magnesium solute atoms here, depicted in red, are uniformly dispersed throughout the aluminum matrix, which is colored in blue for this illustration. As the specimen is plastically strained, these magnesium atoms, which are slightly bigger than the aluminum atoms, they diffuse toward the tensile region of edge dislocations in the metal. Here they pin further dislocation movement until the bondage of those solute atoms itself is broken. Now, while they're pinned, we see the stress rise. And then when they break free, we see what's described as a plastic avalanche of the localized band. At this point, there's a burst in the dislocation movement and the stress suddenly falls. And then again, as this process repeats, this is what we observe and call the Portevin-Le Chatelier effect, more commonly the PLC effect. And again, the reason why we see this in 5000 series alloys is because the magnesium atoms are in solid solution with the metal. And so they're able to travel until they're pinned. This differs completely from 6000 series aluminum, which is also alloyed with magnesium, but in 6000 series aluminum, the atoms are tied up in precipitates that are not able to move throughout the aluminum matrix. So this is that same test from before, the 5182 alloy, and it's exhibiting the PLC effect through the strain hardening region. Here, instead of looking at a stress strain plot, I've chosen a Blue Hill chart that shows R value plotted over time, as well as the contributing strains over time. And then I've highlighted the domain that's used for plastic strain ratio determination for this alloy, which is 8 to 12% axial elongation. In this area, there's almost 9% variation over the range. So depending on which points are actually chosen for the calculation, you can get large swings in variation test to test. Looking at the plot on the right, we see that the source of that variation is the stepped behavior of the transverse strain measurement. Again, it's capturing the width strain as a band passes the single width transverse extensometer, but it's missing the width strain when it occurs anywhere else. And I've recopied the R value formula here again, just as a reminder of how these measurements affect our calculated R value. B naught is the original width of the specimen, and B sub 1 is the width after the specimen has been strained. So here what I've done is I've zoomed in on the region where R value is calculated. So the 65-second mark corresponds to 8% axial strain, and the 75-second mark corresponds to roughly 12%. So we see the direct contribution of the stepped green transverse strain plot and how it affects the teal calculated R value or plastic strain ratio. So looking at a single point, the 10% axial strain that I've highlighted here in yellow, we see that R value increases with an observed increase in transverse width because the metal has shown its ability to stretch in plane. But then as the localized width strain occurs elsewhere, and we have the plateau in the transverse strain curve, R value is perceived to decrease until a band crosses this width again. And this behavior is consistent across the 5182 alloy specimens we tested. In speaking with producers at the time, we were told that in order for them to ensure they met formability requirements, they essentially had to plan for the very bottom of the range of R value in order to avoid producing non-conforming material or material that required multiple retests. Now, in order to do this, they would work to lower composition levels of magnesium, although this would prevent them from, missing their R value requirements. It meant that they were sacrificing strength to do that. And still, they were delivering material with lots of variation in the certified value. And so here's a look again at those same tests. And what we're looking at is the contributing axial on the right and transverse on the left strain data for these tests. This really demonstrates the consistent unpredictability of the transverse strain behavior that's directly contributing to the variation in our R value. You'll notice that my plots are all offset so that we can easily see how each test progressed relative to the other tests. This is possible using a simple toggle switch in Blue Hill that I use regularly when I'm reviewing test-to-test data. And then for contrast, I wanted to show a similar test that was done on a 6000 series alloy. Specifically, this is 6063, and it does not exhibit the PLC effect. As I mentioned before, though, it unfortunately doesn't exhibit a lot of work hardening. For this alloy, we see smooth stress strain plots and the accompanying smooth R value determinations with very little variation in plastic strain ratio test to test. The coefficient of variation for R value for this alloy is just 0.38, so much lower than what we saw for that 5182 alloy. And then looking at the transverse and tensile strain data individually, which we can do simply by creating additional Blue Hill charts, they're both smooth, which is how we get the smooth R-value behavior. And then looking very closely at the domain of the plastic strain ratio, we see that there's very little variation across this plot and almost no variation in the single point calculation. So the question that we asked ourselves was, how could we include the width strain behavior all along the reduced section so that we'd not only get a smoother transverse strain curve, but we'd also get more representative R values that would be more repeatable test to test, lab to lab. The solution we developed was a video extensometer that instead of tracking just one gauge width, it actually tracks 32 gauge widths along the specimen. So this captures the width strain behavior wherever it happens within the gauge length, and it averages the result into a single value. This Instron developed technology called AVE3 and this approach is accepted both by ISO and ASTM. And the most recent version of 10113 was actually published with language recommending this approach as a way to obtain more reliable characterization of R value. Now, another great advantage of using the AVE3 technology is that you also gain the advantage of the environmental conditioning capability included in the AVE3 extensometer. This extensometer uses Instron's proprietary technology called CDATs, or constant density air tunnels, to control the airflow between the camera and the specimen. By controlling this airflow, we're able to reduce the noise in your strain data, delivering the most reliable, repeatable strain data for a video extensometer. And then with the AVE3 technology, which again, it's an optional feature to add on to the AVE3, this technology uses markless edge detection to track the width strain across all 32 gauge widths along the gauge length. So this provides the highest resolution width strain, ensuring that wherever strain occurs, it'll be captured and averaged into the result, giving the most repeatable R value determination possible. And by using markless edge detection, there's no need to apply any transverse markers or flags. So now let's look at the effect of using this method. Although we still see some of the characteristic jerky flow in the stress strain plot, the important thing is that the oscillation in the plastic strain ratio has been dramatically reduced. This is because the transverse extensometer is now taking into account the localized width strain across the reduced section and averaging it into a single result. Here we see that the plateaus in the transverse data on the plot on the left, they're significantly shortened because we're now calculating width strain with much greater resolution along the gauge length. Zooming in on the zone relevant to plastic strain ratios calculations, we see much smoother transverse measurement. The variation in R value has dropped across the zone, and now you have a much more reliable indicator for single point R value calculations. Here's a look at R value calculated throughout the test, along with the corresponding transverse and axial strain. Much less variation than with the single point method. And then so in summary, here's the side-by-side improvement going from a single width gauge measurement to a multi-width gauge measurement. The meaningful effect this has for the producer is that they can dial in their magnesium composition for improved strength while maintaining confidence that they'll get reliable, repeatable R values, compliant with the latest test standards. Now, I should note, although 5182 was the alloy of choice for this research, this approach is suitable for improving the reliability of formability characterization for any alloy exhibiting the Portevin-Le Chatelier effect, or the PLC effect. And then as a sort of bonus slide here, I mentioned earlier that I was going to touch on advanced high-strength steels. So I wanted to note that we also see benefits of applying this method to complex ferrous alloys, like advanced high-strength steels, although for a very different reason. Advanced high-strength steels are not PLC affected, but their complex microstructures generate more heat during plastic deformation, which tends to localize strain in the specimen, causing non-uniform deformation. Now, depending on where this localization happens, width strain will vary relative to the location from a single point extensometer. By using the multi-width method, these results become much more repeatable. So with that, I want to thank you for taking the time to listen today. I'm happy to answer any questions with the remaining time that we have, and would love to connect for anyone that would like to reach out.
Thank you so much, Dean Lovewell of Instron, for that excellent presentation. Let me take the slides back here. So yes, that was Dean Lovewell, Metals Market Manager for Instron. And for our audience, please do enter your questions into the webinar player on the questions tab, and we'll take as many as time allows. So let's dig right in. Dean, first question. Could this approach influence how we interpret historical R value data that were collected using single width mechanical extensometers?
Thanks, Bob. Yeah, that's a really good question, because there will certainly be a change, and that change will be that there'll be much more repeatability at the mean R value from historical tests. So the standards do recommend that in your certification of material, that you acknowledge whether you're using a single width gauge or an averaging method. Now, for aluminum alloys, we'll see that concentration around the mean, because again, we're not changing the level at which R value is calculated. We're not expecting it to be higher or lower. We're expecting it to follow much more closely to the average and really the representative representative plastic strain ratio for that alloy. So good question.
So our next question is average 32 suitable for clear materials? That is an interesting question, and I would encourage the questioner to reach out. I think it would be appropriate for me to direct to one of our plastics experts here at Instron. I have not worked with metal specimens that are clear, but there's a lot of advances in metals, so I don't want to rule any out. Great. Okay. Our next question: when you subtract the elastic strain, does it mean you subtract width elastic strain from width true strain? What about the thickness elastic strain? So that's a good question, because so two parts. Yes, we are subtracting both the elastic width strain as well as the elastic axial strain. We actually don't have to do any subtraction for the thickness strain, because we're not measuring that directly. It's inferred by the law of constancy and the measurements that we are taking. So we're not directly subtracting the elastic strain from the thickness,
but it is not included in what is inferred from that formula.
Okay, thank you, Dean. We're speaking with Dean Lovewell of Instron. Does the same averaging principle apply to advanced high-strength steels where strain localization is thermally driven rather than solute diffusion driven?
Yeah, that's a good question, because the averaging applies in the context that we're obtaining a more repeatable and representative R value, but the variability that we're removing is somewhat different. So with a PLC affected alloy, we're seeing width strain move along the gauge length of the specimen in these Luder's bands that you see on the specimen itself. For advanced high strength steels and other complex microstructures where the strain localization is due to the thermal characteristics, so a part of the specimen getting significantly hotter than other parts, here we're not seeing that width strain move around the specimen. We're seeing it preferentially in one location. So with advanced high strength steels, by using the averaging method, you're accounting for the part of the specimen that is seeing that rise in temperature, and so it's seeing the greater width strain. You're also accounting for the part of the specimen that would be closer to the gauge marks, closer to the shoulders, where width strain is likely not concentrated. The important distinction there is I mentioned in the previous answer that using an averaging method doesn't change the mean for an aluminum alloy calculated in this way. For an advanced high strength steel, you would actually expect to see a lower R value for the metal when tested with the method. Now, why is that desirable? It's desirable because it's reflective of what the material is doing, but understandably, it requires some explanation if you're going from a single width method to the multi-width, where you would want to clarify that in your certification documents. And you'd also want to discuss it with the former to understand that the plastic strain ratio or the formability of their material is not actually decreasing, it's just being more accurately represented. And if I can help in that communication, please don't hesitate to reach out. These are just the types of things that I like to get involved in my role.
So just a reminder to our attendees, tomorrow, about 24 hours from now, you're going to receive a follow-up email. It'll have a link to the recording of this session and attendance certificate. And I'm also going to put connection info for Dean in there as well. So if there's anything you do want to follow up on, you'll have that info. Should come to you about 24 and a half hours from right now. There was a bit of a follow-up on that question about clear materials, and I don't know if this changes what you want to respond. I know you did want to connect with this person offline, but they said that question was about calculating Poisson ratio for plastics.
Yeah, I definitely want to connect this person with one of our plastics experts. One of the luxuries or curses in my role, depending on how you look at it, is that I'm a metallurgist here at Instron, so I'm very concentrated in our metals testing applications. But I would certainly caution any answer I would give on a plastics product. But I have teammates that are as focused on plastics as I am on metals, and would certainly like to connect you with them.
Great. So our next question is, how do we determine whether a material is exhibiting the PLC effect? Is there a list of these materials?
Yeah, so I will say that the materials that exhibit this, the behavior is well studied, because it is a frustrating behavior. So the simplest thing is that if it's a known alloy, you can search for it, and it will certainly reveal other studies on that material about the PLC effect for that alloy. The other thing that you could do, perhaps this is a novel alloy or a novel application of that alloy, if you were to run in a displacement control test, just at a test with a crosshead speed to see the stress strain curve as it unfolds. If you see the sawtooth characteristic in between yield strength and tensile strength, where you have a rise and fall of the stress value during strain hardening, then that is almost surely evidence that the material is PLC affected. And I'll note that not all PLC affected materials are PLC affected through the entire region of their strain hardening region. Some of them reach a threshold by which the solute atoms no longer pin, and it deforms continuously preferentially. 5182 is a classic example of an alloy that shows this behavior the whole way. So the short answer, again, is that if you search by the alloy name and PLC effect, if it is PLC affected, you will certainly see content on it. If you're not sure and you can't find the alloy name, you can run a crosshead speed controlled test. And if you see the sawtooth behavior, it's almost certainly a evidence of either the Portevin-Le Chatelier effect or another form of dynamic strain aging. Dynamic strain aging, which is often discussed in the context of nickel alloys as well. And there's discussion about how much those alloys are affected by PLC versus straight DSA. So.
Thank you, Dean. We still have a little over 5 minutes left, plenty of time to take a few more questions, but this is around the time that attendees start to drop off. So I do want to remind everybody that if before you leave, please do go to the handouts section of the webinar player. There are data sheets for 2 of the products that were mentioned today in there. You definitely want to download those before you exit. So moving on to our next question. What if there is strain reduction difference on the left and right side of the specimen? How is average 32 handling this? Horizontal lines may shift diagonally, right?
So if there is a shear component to the specimen, so for example, the right side would be straining more than the left. Is that? I think that's the question. So the width that's measured is strictly the width perpendicular to the length of the specimen. So if you have dominant shear behavior where one side of the specimen is straining more than the other, then you're not going to follow along that diameter. You're going to follow the resulting width that occurs even with that sort of angular strain within the material. And the reason for this is that this is how the standard is written, where we're strictly following the width as we've detected from the edges, rather than following specific marks. Following specific marks would be more of a DIC application.
Okay, our next question. What would alert the tester that the curve is exhibiting PLC rather than noise?
Yeah, that's a really good question. What I would be inclined to do, and this is one of the first things I do when I look at a PLC affected alloy, is to use the test software. So in our case, we use Blue Hill Universal, and we can establish charts that show my axial strain behavior as well as my transverse strain behavior I used that chart a couple of times, and what's important about that is that you're separating out the constituent components of the R value into what really evidences PLC. So if it's a PLC affected alloy and not just noise in your system, the axial will look relatively smooth. Again, PLC affected alloys always have somewhat jerky behavior because of this pinning and unpinning that occurs at the microstructure level. So, but the axial strain will look relatively smooth, kind of that exponential ramp. The transverse data, on the other hand, will be stepped if you're using a single width gauge like the extensometer. So you'll see a momentary increase in the width strain, and then you'll see a plateau followed by another increase. And that would be a pretty definitive way to separate out that you're working with a PLC affected alloy.
Okay, are there recommended best practices for specimen preparation or lighting when using optical transverse strain measurement to minimize error sources?
Yeah, that's a really great question, especially given the fact that we're in the field of video extensometry, where things like that can be a concern. Now, the good news is that we have designed our video extensometer, the AVE3, to work in all types of lab environments. So you don't need to pay extra attention to the lighting. The luminosity is designed to work through those conditions. The surface condition of the specimen is important. For example, if you have a scaly specimen, like a hot roll product, from a hot roll sheet mill, the scale on that specimen will tend to flake off. This interferes with the edge detection because that scale actually makes up a part of the width, but is then suddenly lost. So that would give a lot of variability in the data. The way to work around that would be to only use this on hot roll product that had been shot blasted or pickled sufficiently to remove that scale so that it's not flaking during the test. But in terms of the luster of the material, we have proven this out and verified it on shiny material, galvanized product. So it is robust. It is designed for the use for steel products. So if you are testing steel products, then you should feel empowered to take advantage of it.
Dean, guess what? We're out of time.
Ah, rats.
and out of questions. So it happened perfectly this time.
Perfect.
So thank you, Dean Lovewell of Instron, so much for this excellent presentation and Q&A session. Oh, you know what? We did get one last one in. Do you have an extra second?
I sure do.
What is the optimal marking material for DIC points?
The optimal marking material for DIC points.
Right.
Well, unfortunately, that is another question that I am going to have to discuss with our strain product manager. I've seen different methods here, anywhere from decals that are applied to the dots being sprayed on. But I will reach out to our strain product manager, and Bob, if you'd be so kind to provide me that contact information, I'd be happy to get an answer to this person.
Absolutely. I'm going to send you all the questions about 5 minutes
Great.
after we're done.
Terrific.
Here. So
thank you.
Great. So once again, thank you to Dean Lovewell of Instron. All of our attendees are going to receive a follow-up email about 24 hours from now. There'll be some contact information in there. So if you want to get in touch with Dean, you'll be able to do that. Also, I want to remind everybody one last time before we exit that there are those 2 downloads in the handout section. Please do grab those before you exit today. And once again, I'd like to acknowledge the sponsor of today's webinar, that's Instron. You can direct any general questions to instron.com/en us/our-company/contact us. You can see it on the screen there as well, or maybe just wait till that email comes with that contact info tomorrow. More information, of course, can be found at instron.com. And finally, thank you to all of you for joining us today. We certainly encourage you to complete the brief survey that's going to appear on your screen right before you exit. And with your help, we can continue to provide webinars with high quality, practical information that you can use. Thanks again to our speaker, to Instron, and all of our attendees today. Have a great day, everyone.